Hello, let's get started with lecture 9. And last time we looked at the driven harmonic oscillator. As I said, this is basically a quantum field theory in 0 dimensions, in 0 spatial and the one-time dimension. So quantum theory of a dot. However, of course, we are interested in theories that would live in our 3+1 dimensional space-time. So we dive into this topic today. But let's talk first about how to construct interacting Lagrangians of such theories. What are the rules we have to follow? We said already earlier that in our natural units, the action has dimension or mass dimension 0. Then the operators, the terms in Lagrangian, have to respect the Lorentz symmetry. They have to be singlets. They have to transform like a so-called singlet under coordinate and Lorentz transformations. And the operators have to respect internal charge symmetries. We discussed it in the context of complex scalar field, where we could explicitly multiply it by a complex phase, and that is an internal symmetry of the field, and all the Lagrangian terms have to be invariant under this symmetry. So we know how the scalar field itself transforms under the Lorentz symmetry. So far we dealt only with scalar fields, so we will stick to this. And what kind of terms can we construct that are also transforming in the same way under the Lorentz symmetry? This is the well-known kinetic term where the Lorentz symmetries are contracted. So it's a Lorentz scalar because if we do a Lorentz transformation, those two fields transform in such a way that their scalar product is invariant. This is the way we constructed the Minkowski scalar product. Also, if we have a complex scalar field, the square of it transforms also as a scalar, and the complex conjugate times the field itself is a singlet, or doesn't transform if I multiply both with the same complex phase. However, such a term where you have 2 times phi star for a complex field would not transform properly as a singlet. Under a phase multiplication, you will get a term something like e to the minus I 2 theta if you multiply each field by e to the minus I theta. Right, so this transformation would not leave this invariant, so this is a non-admissible term for Lagrangian. This term, for example, here, if we have a constant vector A multiplying the derivative of the field phi, which transforms as a vector actually, but this combination would not necessarily or would not be Lorentz invariant, because A stays constant, but this transforms as a Lorentz vector, and then this product will change depending on the frame I choose, which is not admissible either. So what we can do is writing down a certain structures in terms of terms. So one would be this derivative term. Then we could have this term where we have the square of the field. For a complex field, we have to take the phi times phi star, but never mind, let's think of it as a phi absolute value squared if it was a complex field. And here, this one is the known mass term, so the overall part here is called the free Lagrangian, as we discussed in the previous lectures. And now all the interactions we can think of can be written down for this real scalar field as just powers of phi with some coefficients, where this factors n factorial is only a combinatorial convention factor. Yes, so the main thing is that we have just some phi field product that goes to a power n, and those all transform as Lorentz singlets under Lorentz transformation. Here n runs from 3 and in principle up to infinity. It respects the rules that we have just defined. Now remember again, the action is has mass dimension 0. This measure here is mass dimension -4 because it's length to the 4th power. So the Lagrangian density has to have mass dimension 4. We know that the derivative has the mass dimension 1 because it's inverse length. So even from the first term, for example, we know that the phi has to have mass dimension 1 as well. That means that all the coefficients in this sum here have to have mass dimension 4 minus n, right? Good. So some of them will be dimension, will have positive mass dimension, some of them will have negative mass dimension, and if n is exactly 4, this mass dimension will be exactly 0. Now we want to treat this new terms as small perturbations of h naught. We discussed it with the example of the driven harmonic oscillator. This is essentially the technique that we know best when we can expand around the free solutions and have small perturbation. And let me just show you that there's 3 important categories of terms here. The first one, where the mass dimension of this coefficients is 1. So if we want to have an expansion parameter, to say a parameter is small in mathematical sense, to use it as a small parameter expansion, we can only work in unitless numbers. That means they cannot have physical dimensions of length or mass. So since we know that the parameter in Lagrangian has mass dimension 1, we have to construct an expansion parameter that is this lambda tilde divided by some energy. So our expansion parameter that is dimensionless will depend inversely on the energy. And now we can expand our theory in terms of this lambda 3, and this will be the measure of how small the perturbation to the free theory is. So now we see this term in Lagrangian has this lambda tilde. So it is actually small when the energy is large. Yeah, when the energy is much bigger than this lambda tilde. So if we probe the theory at large energies, this term is not that relevant, but it becomes relevant or becomes bigger when the energy is actually growing smaller and smaller. So at low energies, this term is relevant. Hence the name. This is a relevant operator or a relevant perturbation to the theory that this becomes relevant when the energy drops. The next one is lambda 4. Lambda tilde is dimensionless, so this is fine. We can just keep our expansion parameter as lambda 4 is lambda 4 tilde. And we don't have any strong scaling with the energy of this. We will discuss in the future that there is some scaling possible of such operators as well, but we need more work than that to see that. However, the scaling cannot be very striking here, and those operators are called marginal. Now, if the mass dimension is smaller 0, for example, for n larger than or equal to 5, well, now we have lambda n, the expansion parameter, has to go as lambda tilde to the power e to the 4 minus e to the n minus 4, where n is larger or equal to 5, so it scales proportional to energy. Now, if we have now this lambda tilde terms here, we see that the lambda tilde itself would then be inversely proportional to E, right? For all n equals or larger than 5. And that means that those terms will be dropping when the energy is growing. Yeah, so those terms are called irrelevant. That means when we go to large energies, they become increasingly less if we go to large energies, they become relevant, or they will become stronger at large energies. But when we go to small energies, those terms will become more and more negligible, in fact. Right? So they will become irrelevant. So these operators are called irrelevant, always from the perspective of a low energy theory. We now have seen how those operators are classified in relevant, marginal, or irrelevant operators. And later we'll also see that those irrelevant operators are related to so-called non-normalizable theories. And one can think of those theories in a sense as being incomplete and not showing the full picture at the low energy that we are studying the theory at. And then one still expects that at a larger energy you would have something that renders this theory that augments the theory, and I will give you an example of this in a second. So the question again is why QFT is so simple. I mean, you might say it might be not super simple, but it could be much worse. Yeah, why is QFT not as bad as it gets with all these possible terms? So let's just assume for a moment that we discovered the theory, the super theory, all the irrelevant operators that has our free Lagrangian, the marginal and irrelevant operators, marginal and relevant operators, and all the irrelevant operators as well, and they all live at some scale lambda. We can now write down all these irrelevant operators with these factors, with these explicit factors lambda n, where we factored out the mass dependence that we have derived as some sort of large scale lambda at which this full theory is operating. So for n equals larger than 5, those terms will be small if lambda here is much larger than the energies that we can probe the theory at. So we explicitly pulled out the scale dependence in lambda and have such that we have those coefficients being just numbers of order 1. Right, so every experiment we can do is at much lower theories than lambda, and all these factors then are suppressed by factors of e divided by lambda to the power n to the minus 4 for n larger than 5. So for an example, the LHC has an energy of 10th of TeV, while the Planck scale is at 10 to the 19 GeV. So we have something like 10 to the 16 TeV, or if the LHC is rather the TeV scale, and this is the Planck scale at 10 to the 19 GeV being 10 to the 16 TeV. The ratio of those scales is about 10 to the minus 16. So even the lowest power operators that would be induced by some sort of physics that lives at the Planck scale would be suppressed by 16 orders of magnitude. To the next contribution would be suppressed by 32 orders of magnitude, and so on. Of course, if the new physics is arising below the Planck scale, we could have much stronger effects. Now, to the point of the incompleteness, let's have a look at this interaction. Just an example, the 5 to the 6 interaction that I said is an irrelevant operator. And now imagine that we have in our theory several fields, and then we have marginal operator. We have a field phi cubed times psi, both real fields. That now psi is very heavy, very much heavier than the theories we can study. Now we will come in a second to how we can think of diagrams, and that will help us studying field theories. Let's draw a diagram like that. So this interaction will be connecting 3 phi fields in a psi field, and then you also draw it twice and connect those interactions with the psi field itself. You know, the one thing we have learned before is that we can represent this kind of lines where you propagate the field from A to B as this propagator in momentum space, where we have the inverse of the momentum squared minus the mass squared. So this term, roughly represented by this diagram, can be written as the couplings constant squared phi cubed psi phi cubed. So now this one will be replaced by this propagator, and assuming that our momenta at which we can probe the theory are much smaller than this mass of the psi field, we have something that goes like lambda squared divided by m psi squared phi to the 6. So now you see that this operator is really suppressed by the from the low energy perspective, this operator is suppressed by the mass of the psi squared, and we think of it as an irrelevant irrelevant operator. It doesn't affect our physics terribly much. But now once we go into larger and larger energies and eventually have momenta of the order of psi, p's of the order of psi, the momentum at which we can make experiments, we will then resolve this interaction that looks actually irrelevant, and it would become a marginal operator that actually contributes significantly at scales of the order of the psi field. And then, however, again, the theory that we are actually evaluating at that energy looks pretty simple in the sense that it only has this kind of lower few fields multiplied with themselves. So in that sense, when we go to the energy scale where we can really effectively test interactions, the operators playing a role there will be the relevant and the marginal operators. And other contributions to the theory that might appear complicated with many interactions would always be suppressed with respect to the scale we are actually probing the physics at. That is also the reason now, so let's have a few examples. This is also the reason why the theories that we study here are actually pretty handleable. And since we will not worry about the irrelevant operators, but only look at relevant and marginal operators in the interactions that we have to consider here. Again, let's take a look at this example. Let's call this scalar Yukawa theory. Yukawa was a physicist. He was studying the strong nuclear force in the interactions between nucleons and mesons, and found that there is scalar particles in the theory that mediate the strong nuclear force. He called them mesons, and they exert a so-called Yukawa potential. We come to that in a while, and hold, for example, the nuclei together. It's a scalar. I call it scalar Yukawa theory because we don't have fermions. I mean, nucleons are usually fermions, like protons and neutrons. But we don't care too much about this now. The structure of the theory is still such that you have a force carrier coupling together two fields, and we will see how it works. So one part is the free kinetic energy of the fields of the complex field psi and the real field phi. Then there are the mass terms for the complex field and the mass term for the real field. And so the only interaction, the relevant interaction, has psi star psi times phi. Now, if you remember our treatment of the harmonic oscillator that was driven, we basically replaced now this external force J by this product of psi star psi that can be seen. It is also called current, but you could also think of it as an external perturbation that is now resolved in terms of another fundamental field. And that field interacts with phi, it can have an effect on phi. So you can see the analogy to the driven harmonic oscillator here that we were studying last week. Of course, it's a quantum field theory, particle number is not conserved, but there is a symmetry. Psi goes to e to the I theta psi, and that's why the psi charge is conserved. So the charge operator commutes with the Hamiltonian, and psi has antiparticles, as we also discussed. We can call them psi bar for notational reasons. And so Q is just the number of psi quanta minus the number of psi bar quanta, and this is a conserved quantity in the theory. Another example is so-called phi to the 4th theory. Free Lagrangian, as usual, and only marginal term is this phi to the 4. And so we will also see why it's interesting in certain contexts. Just as an example here, you can see expand for lambda being small, we can expand phi in the usual free ladder operators A and A dagger. And then just by having this phi to the 4 terms, we can have 4 creation operators or 3 creation operators in this expansion. And we can see that in this theory, the quantum number is really absolutely not conserved, and explicitly this interaction term can create new field quanta and lead to excitations of the field, of course. Now remember, we are interested in transitions that are induced by interactions, and we have defined last time the so-called S matrix, this unitary operator that goes from minus infinity to plus infinity. So it takes the initial state to the final state formally, and the transition element between the final and the initial state can be written as this product matrix element or overlap element between the final and the initial state with the S matrix operator wedged in between them. And it is the square of those matrix elements are of those so-called amplitudes represent the probability to have a transition from the initial to the final states, and those are ultimately related to our physical observables. Well, we know that S is unitary, which means S dagger S is equal to 1, and this has to be the case because actually, since we want these squares to represent probabilities, by Kolmogorov's axioms, all the possibilities and probabilities of all things that can happen have to sum up to 1. We saw actually a representation for this S operator, this scattering matrix operator, as this exponential of the integral over the Hamiltonian, the interaction Hamiltonian, that has a time ordering part here. We see that since this is the integral over the Hamiltonian over time, the Hamiltonian is actually integral over the volume of the Hamiltonian density. And that means that this is actually the 4 space-time integral over the Hamiltonian density. Then we know that the interaction Hamiltonian is just, there's just a sign difference from the interaction Hamiltonian to the interaction Lagrangian. So we actually can also write this as this exponential of the integral over the interaction Lagrangian with a time ordering operator here. Ultimately, this is only defined in terms of a power series for operators. And again, the power series can only be evaluated term by term. The first one is obviously just 1, and then we have 1 integral over the Lagrangian density at a space-time point x, and then we would have an integral over 2 L's, and so on, 3, 4, and so forth. Now our goal is to develop a method for evaluating the scattering amplitude, and then we will rely on this perturbative expansion, assuming that the interaction is small compared to the free theory. And we will use a very powerful technique developed by Richard Feynman, who showed how to find this kind of series expansion, the terms of the series expansion, using a very intuitive way of drawing diagrams. Let's go back really quickly to this Yukawa type scalar Yukawa theory. So this interaction then only represents field interaction like this, phi, psi bar, psi bar. And if you introduce now the time direction, this would represent, for example, a decay process of the field phi decaying into two field quanta psi bar. We can combine such diagrams, to, let's say, higher order. We will see also how they are related to the orders of the expansion, such that we have scattering. Psi bar goes like this, exchanges a phi in different ways. We also discuss why and how it is relevant. Also, the psi can run in loops, which can cause potential trouble, and we will also learn how to deal with that. But there are many possibilities to connect those fields. Ultimately, the goal is to find a way to use those intuitive diagrams to represent processes and make them connected to explicit mathematical structures to be able to calculate the processes in quantum field theory. Now we are approaching the point where we can evaluate our first QFT amplitude. Now remember, again, the scalar field theory has just this interaction term in the Lagrangian. And we are interested in this decay term that I drew before, phi going to psi bar psi. They have momenta. Phi came in with momentum p, and the outgoing fields have momenta q1 and q2. Now, so far we don't know how to use any of the fancy techniques yet, and we will just do a very pedestrian way of showing this. So let's write down the first terms in the expansion of a series. So it's 1 and minus I integral d4x of this interaction Lagrangian term. This is just the interaction Lagrangian, phi, psi bar psi. Now we need to construct their initial and final states, and the initial state, we know how to do it, is constructed by the creation operator with a p acting on the vacuum, and then there's a relativistic normalization factor here. And for the complex scalar field, we have two different operators, one for the particle psi and one for the antiparticle psi bar. So we have C and B dagger creation operators with the momenta q1 and q2, and the relativistic normalization factors here. So evaluating this amplitude, so the wedge bit of this scattering matrix between the initial and final states, we write it down. We can immediately pull out the negative IY just as a number out of this product. And then we have the final initial state and this integral of these operators in here. So we know how to deal with this. We start by expanding phi in A and A dagger. We know that the annihilator A acting on the initial state the initial state has one creation operator of the field phi, and the annihilator of the field phi here will lead to the vacuum state being left over. If we add, however, a creator of the field phi, there is already a creator of the field phi in this state here. So in the end of the day, we will have a two-meson state. But the two-meson state has no overlap with the final state, which is the psi fields, right? It has zero mesons. And we call those, let's call the psi's nucleons and the phi's mesons. So there's no overlap of this two-meson state. So it means that this contribution doesn't contribute, and only the contribution where we have the annihilator A acting on the initial state will give us something. So let's just write down this contribution. So this state as before, and in this field expansion for the field phi, we have the usual measure with the relativistic normalization factor, and then we integrate over k, e to the ikx, here's the annihilator with the momentum k, and this is the creator of the initial state, phi, particle with momentum p. So we can use the commutator, flip them, so we get a dagger a term and plus the delta function. A dagger a acting on the vacuum vanishes since there is an annihilator meeting the vacuum, and then we have only one term which we can evaluate by integrating over the momentum k, which sets k equal to p, yeah. And we are left with this term. And we are left with just this term where we have, in fact, this should be a p. However, they are equal, but it's nicer to keep the p momentum in this expansion. So yeah, because of this delta function, the k is set to be p. Now we have to work with these psi bar psi terms here. We plug in the expansion. They look a bit lengthy here, but we can plug them in and see which terms at all can contribute, right? So we have to create, since we have the vacuum here now, this is a number. We have the only way to have something that has a non-zero overlap with the vacuum is to create and annihilate the equal number of numbers of particles. First of all annihilators meeting the vacuum immediately will annihilate it, so this term will be gone. So the only contributions come from here. So we have B dagger, C dagger, B, C. This is the only combination of those, all of those four terms that are possible that will actually give you a non-zero contribution. So here we have B dagger, C dagger, B, C. And then we can commute it, apply the commutator twice. First we flip, for example, the C and C dagger, get one delta function, and then we've also flipped the B and B dagger and get these two delta functions, setting Q1 and K2 and Q2 and K1 equal. We can perform both of these K integrals, which are will be leaving us only with this exponential, so this will be set to 1. So we'll be only left with this exponential. The products of the vacuum is 1, and the exponential integrated over this d for x is just that as defined, the delta functions times 2 pi to the 4 because of this exponential here, and that sets k plus k1 plus k2 equals to p. And yeah, k1 and k2 are equal actually to q1 and q2, which are the momenta of the outgoing psi particles. So what we have left, what we are left with is just negative iy, the interaction strength, 2 pi to the 4 times the delta function that conserves momenta. And this is our first QFT amplitude that we completely computed. Essentially just using creation in the annihilation operators. Let's think for a second what actually this delta function here means. It imposes some kinematic constraints, and to study what it is, we can just go to the rest frame of the decaying particle. Let's say, yeah, the phi decays, and let's say it is at rest. So the spatial momentum components are 0. The energy is just m phi in our natural units, and after the decay, the psi1 and the psi and psi bar has to go back to back, and they have equal and oppositely directed momenta, because momentum has to be conserved and has to add up to 0, because it was 0 in the beginning. So yeah, one has, let's say, if one has momentum q1, the other has momentum minus q1, and we know that the energy is also conserved, so we can say m phi, or basically the delta function now setting this four momenta equal to each other tells us that since this is 0, it's just that the first component is actually the only condition we get, which is the energy conservation. So m phi is equal to twice square root of m psi s squared plus q squared, which is the momentum of the outgoing particles, which is a strict condition that m phi has to be necessarily bigger than 2m psi, which is absolutely clear, because if we want the phi to decay to 2 psi's, like psi and psi pi have the same mass, we have to have more energy, or in that sense more mass, in order for the process to be allowed. Otherwise there's just not enough energy to create the 2 psi particles. Yeah, so this is just a kinematic condition that conserves energy and momentum. And the interaction strength, or as we said, the probability for things to happen, is proportional to the square of this amplitude, and we will discuss how to deal with the square of delta functions later, but the probability will be proportional to this parameter squared, which is called the coupling strength, and that means that this interaction or the decay probability will scale as this coupling strength squared. Also, this explains why we call it a coupling, because it having the possibility to make it larger or smaller controls how strong the interaction is, and for example how fast and this decay will happen. Faster when I increase this coupling of the phi to the field psi, which is all for today. And yes, so we have learned how to construct Lagrangians based on the conservation laws of internal symmetries, and that the fact that they have to respect Lorentz symmetry. We have found which operators are relevant or marginal, but which operators are needed to be considered in order to study the most important interactions. When we assume the couplings to be small, we can expand in a perturbative way. We have a well-defined series that tells us how initial and final state can convert from one into another, so we can study physical processes. And ultimately we have computed our first QFT amplitude that describes a simple decay, but we already learned several things there, like the energy momentum have to be conserved, and how the coupling strength influences the strength of this, or how fast this decay process will proceed. Great. And next time we will go into more detail and study how we can use much more elegant techniques to study those processes that we have done here in a very clunky way.